Welcome to my presentation with the title, Joule or Newton, that is the question. The benefits of mechanical control elements in automotive user interfaces. My name is Manuel Kuhner and I am a haptics engineer. I used the same slides to give a presentation at a conference called Smart Haptics in Seattle on December 7, 2022. Although I was employed by a company called Woven Planet at the time, the content of this presentation represents my personal opinion only. I start the presentation by motivating the topic. Then I will mainly discuss three aspects of control elements in sections 3, 4, and 5. In the motivation section, I want to explain why the topic may matter. Using a touch-based device such as a tablet or smartphone is common in consumer electronics. Typically, the user gives their full attention to the touch device, or in other words, using the touch device is the primary task for the user. In contrast, in the context of driving a vehicle, driving the vehicle is the primary task, and using the touch device is the secondary or tertiary task. Therefore, using the touch device is a potential distraction from the primary task. Please refer to references 1 to 3 for more details on the classification of primary, secondary, and tertiary tasks. Please note that the Society of Automotive Engineers (SAE) uses the term dynamic driving task (DDT) instead of the term primary driving task. This diagram shows the number of deaths caused by motor vehicle crashes in the U.S. for the years 1975 to 2020. Overall there is a positive trend, meaning fewer people die per year. However, since 2014 there is a negative trend, meaning more people die per year. According to a 2022 documentary from CNBC, distraction due to touchscreens could be a factor that contributes to this negative trend. This is a potential motivation for reducing distraction from the primary driving task. There are many more examples of negative press for touch-based interfaces in the automotive domain. You can see some examples in the animation on the right-hand side. The PDF version of this presentation contains more references if you are interested. This is the 2022 CNBC documentary that I mentioned on slide 5, the slide with the accident statistics. Johnny Ive was the chief design officer of Apple for nearly 3 decades until 2019. ADAC, which is based in Germany, is Europe's largest automobile association. The headline says, "Distraction in the car, when operating the car becomes a danger." Now that the motivation is clear, I want to briefly describe the goal of this presentation. This presentation does not cover the large topic of driver distraction. Instead, the presentation will only cover a small related aspect. The goal is to look at the robustness of control elements against unintended triggering due to shaking hands, meaning real driving situations. I do this by looking at 3 aspects of control elements: the type of degree of freedom, the type of trigger, and the type of shape. Within these 3 aspects, I will spend the most time on the second aspect, the type of trigger of the control element. Before I go into the details, let me introduce myself. I am a haptics expert for requirement engineering and perceived quality for automotive human-machine interfaces, HMIs. Although the term expert is used inflationary these days. My educational background is a master's degree in mechatronics engineering and a PhD in mechanical engineering. My PhD project had a focus on human factors engineering and haptics. Currently, I am working for Toyota in the US. Before that, I worked for Lotus in China, and the 2 German car makers Porsche and Audi. While working for those companies, I was mostly responsible for human-centric specifications for a range of aspects of human-machine interfaces. Examples include passive haptic feedback and passive acoustic feedback for mechanical HMIs, such as mechanical push buttons. Active haptic feedback for mechatronic HMIs such as touchscreens, touchpads, and steering wheels. And specifications related to touch-sensitive HMIs such as touchscreens, touchpads, touch sliders, and touch buttons. Now I will talk about the first of the 3 aspects, the type of degree of freedom of the control element. Have a look at the video in the bottom right corner. The video shows me driving at a speed of 65 miles per hour. You can see that my hand is shaking translatory, which means up-down, left-right, and forward-backward. The shaking of the hand can lead to situations in which I accidentally, meaning, without intention, trigger control elements, such as pressing the wrong push button, or touching the wrong area in a touchscreen. One problem is that the degree of freedom of operating a push button or operating a touchscreen is also translatory, meaning it is the same as the shaking of the hand, which is caused by inertial forces. In contrast, control elements with a rotatory degree of freedom, such as rotary knobs, are less affected by the translatory shaking of the hand. This is why you can easily hold onto a rotatory knob while driving without accidentally triggering a function. The types of degrees of freedom of the control element and the mechanical noise, vibration, are different. We can conclude that control elements with a rotational degree of freedom are beneficial because there is less interference with the typical in-vehicle mechanical disturbances. Now I will talk about the second of the three aspects, the type of trigger of the control element. This is the main part of my presentation. In the automotive domain, three types of triggers are common: touch-based triggers, for example, touchscreens; displacement-based triggers, for example, classical push buttons; and force-based triggers, which I will explain later. Now the question is how these three trigger types compare regarding unintended triggering due to shaking hands. First, I want to propose an objective metric that I will use to compare the robustness of the different trigger types. Based on a simple experiment that I conducted in my own car, I estimate that my shaking forearm, or shaking hand respectively, has a vertical velocity of approximately 0.1 meters per second, or 4 inches per second in crazy units. According to reference 25, I assume that my forearm has a mass of 1.34 kilograms. Together with a velocity of 0.1 meters per second, this leads to a kinetic energy of 6.7 millijoules that is stored in my shaking forearm. So the rephrased question is, how the kinetic energy of my forearm compares to the work that is required to trigger different control elements. I call the required work trigger work. I will not provide any deeper explanation of what energy or work is, this is beyond the scope of this short presentation. You should know that energy, or work respectively, is typically measured in Joule, named after the English physicist James P. Joule. Instead of Joule, watt-second is also often used. You are probably familiar with watt-second, because your electricity bill also uses watt-second, or kilowatt-hour respectively, as the main metric to calculate the energy cost. In case you do not understand energy, then you are in good company. Even the famous physicist Richard Feynman, who won the Nobel Prize in Physics in 1965, did not understand energy. In his famous Feynman Lectures on Physics, Feynman says it is important to realize that in physics today, we do not have knowledge of what energy is. Now we talk about the trigger type called touch-based trigger, which is the same as saying control elements with a touch-sensitive input. Systems, or control elements, that are touch-based, basically measure proximity, or distance, between the finger pad and a touch-sensitive surface. Therefore, virtually no mechanical work is required to trigger such a system. In other words, the trigger work is zero. This means that a system that uses a touch-based trigger has no robustness against unintended triggering, because 0 joule trigger work is required. Now we talk about the trigger type called displacement-based trigger. This trigger type is the most common trigger type in the automotive domain. A classical example would be a simple push button. I divide the displacement-based trigger type into three subtypes. The first subtype is a non-automotive example. It is a push button based on metal springs. The second subtype is very common in the automotive domain. It is a push button based on silicon rubber. The third subtype is also common in the automotive domain, especially in luxury cars. It is a push button based on a combination of a metal dome and silicon rubber. In the following slides, I will discuss the robustness against unintended triggering for these three subtypes. As mentioned previously, the first subtype is a non-automotive example. Subtype 1 is a key switch that is typical for so-called mechanical computer keyboards. Please look at the animation on the left-hand side of the slide. Here you see how this push button works. You can see that it is a combination of two types of metal springs, a linear spiral spring and a non-linear so-called leaf spring. On the right-hand side of the slide, you see the corresponding force displacement diagram, with displacement in millimeters on the x-axis, and force in Newton on the y-axis. When the push button is pressed beyond the so-called point of no return, then the push button snaps and is triggered. In the diagram, the point of no return is depicted as a red dot. The trigger work can be calculated by mathematically integrating the area underneath the force displacement curve, depicted in orange in the diagram. For subtype 1, the trigger work for the push button is 0.76 millijoule. As a reminder, the kinetic energy that is stored in the forearm is about 9 times larger than trigger work for subtype 1. But not only is the trigger work of the push button itself relevant, additionally, I also consider the deformation work of the finger pad. The video shows how the finger pad of my index finger deforms when I apply force on a surface. I found a research article that measured the mechanical properties of finger pads using a nice experimental setup that you can see here. In the PDF version of this presentation, the research article is reference 30. First of all, I am sorry for the busy slide. For now, please focus on the diagram on the right-hand side. The diagram shows the force displacement diagram of a finger pad. For forces below 7 Newton, the finger pad stiffness can be approximated with a constant stiffness of 5 newtons per millimeter. Now, please focus on the equation on the left-hand side. The key switch push button has a trigger force of 0.6 Newton. With a finger pad stiffness of 5 newtons per millimeter, the additional trigger force due to finger pad deformation is 0.04 millijoule, which is a relatively small value. I will now do the same calculations for the second subtype. This subtype is a push button based on silicon rubber and is very common in the automotive domain. The diagram on the right-hand side shows a typical force displacement diagram for this subtype. As before, the red dot indicates the point of no return for this push button. The trigger work is 4.65 millijoule for the push button itself. This is much higher than for the previous push button subtype. The deformation work for the finger pad is 1.23 millijoule, which is also much higher than for the previous push button subtype. The reason is the higher trigger force of 3.5 newtons. I will now do the same calculations for the third and last subtype. This subtype is a push button based on a combination of a metal dome and silicon rubber and is also common in the automotive domain, especially with luxury brands. The trigger work is 2.48 millijoule for the push button itself. This is about half of the trigger work than for the previous push button subtype. The deformation work for the finger pad is 2.81 millijoule, which is about twice as much as for the previous push button subtype. The reason is the higher trigger force of 5.3 newtons. This diagram shows a comparison between all three subtypes. The dark orange color represents the trigger work of the push button itself. The light orange color represents the additional trigger work due to finger pad deformation. Please note that the horizontal red line indicates the kinetic energy that is stored in the forearm. The first conclusion is that the finger pad work is only relevant for subtype 2 and 3. The second conclusion is that the robustness against unintended triggering is highest also for subtype 2 and 3. Only those two subtypes have a total trigger work that gets close to the horizontal red line that represents the kinetic energy that is stored in the forearm. Now we talk about the trigger type called force-based trigger. This trigger type is relatively new in the automotive domain. Apple's 2015 trackpad, which you can see on the right-hand side, is a good example of a force-based trigger system. The trackpad has two types of input, touch, and force, and uses active haptic feedback as an output. The trackpad uses force sensors called strain gauges to measure the finger force. You can see these sensors in the close-up, orange color. The active haptic feedback is generated by an electromagnetic actuator. The actuator generates a horizontal movement of the trackpad surface that feels similar to the mechanical click of a push button. In recent years, several products were released that feature a force-based trigger. This is true for both the consumer electronics domain and the automotive domain. Please refer to references 33 and 34 in the PDF version of this presentation for further information. In the automotive domain, active haptic feedback is typically realized by so-called surface kinematics. This technical term means that there is a moving surface, for example, a left-right movement perpendicular to the finger force direction. In the PDF version of this presentation, references 24 and 35 provide more information about active haptic feedback in the automotive domain. This slide requires some technical background to follow all steps. But don't worry, the conclusion, in the end, does not require you to understand these steps. With that in mind, let's start. In the automotive domain, the trigger force used in force-based systems is between 2 newtons and 4 newtons according to my experience. The second important parameter is the surface stiffness in the direction of the finger press force. In the automotive domain, the surface stiffness for such systems is between 10 newtons per millimeter and 40 newtons per millimeter according to my experience. With this information about the range of the trigger force and the range of the surface stiffness, the range for the trigger work, including the finger deformation, can be calculated according to equation 4. As you can see in red, The trigger work for force-based systems is between 0.45 mJ and 2.4 mJ depending on the combination of trigger force and surface stiffness. This is the final slide for the section regarding the trigger type. The diagram shows the trigger work for all trigger types that I have discussed. From left to right, you see the trigger work for the touch-based trigger type, then you see the trigger work for 3 subtypes of the displacement trigger type, and finally, you see the trigger work for the force-based trigger type with 2 variations regarding trigger force and surface stiffness. Please note that the horizontal red line indicates the kinetic energy that is stored in the forearm. My conclusion is that only the 2 automotive examples for a displacement-based trigger, and the example for a force-based trigger with a high trigger force and a low surface stiffness, require a trigger work that is somewhat similar to the kinetic energy stored in the forearm, and therefore offer relevant robustness against unintended triggering. Now I will talk about the third and last aspect, the type of shape of the control element. Please have a look at this old-timey so-called boombox, a portable radio and cassette player. This boombox is equipped with different types of control elements that come in different shapes and sizes. Different functions have control elements with different shapes. Therefore, you can easily imagine that, after some experience, you can operate this boombox in the dark. This is also called blind operability. Differently shaped control elements lead to a haptic distinctiveness that helps to get closer to the ergonomic ideal of blind operability. Blind operability means that a user can operate a mechanical user interface with little or no visual attention. A user interface that can be explored haptically, consequently, needs control elements that have a high enough trigger work, otherwise, the user would trigger functions unintentionally during the haptic exploration. For example, 3-dimensional shaped control elements, and not 2-dimensional or flat control elements, are beneficial in this regard. This is in contrast to the recent trend in the automotive domain of having flat, clean, and as seamless as possible, surfaces. I will conclude this presentation in the contribution section. If you wonder why I named this section contribution and not summary or conclusion, then I recommend that you have a look at the book Make It Clear by Professor Patrick Henry Winston of MIT. The contribution section has 3 subsections, namely, the good, the neutral, and the bad. Let me start with the good, in which I will summarize my contribution to this presentation in 3 simple so-called take-home messages. My first take-home message is that you should design a user interface for imperfect real-world scenarios that are messy and characterized by, for example, mechanical noise/vibrations and additional distractions due to other road users. Do not design the user interface for idealistic scenarios such as the showroom experience or optimized press release scenarios. In my second take-home message, I propose to consider trigger work as an additional metric when comparing solutions for automotive user interfaces. As far as I know, trigger work is not considered so far. Instead, trigger force is typically used as the main metric in this regard. Hence, the title of this presentation. My third and last take-home message is that 3-dimensional shaped control elements improve blind operability, which reduces the need for visual attention. In this slide, I share 3 considerations that I want you to keep in mind. Firstly, touch-based interfaces in the automotive domain are not all bad. There are also benefits, for example in the context of navigation systems. Secondly, I talked a lot about classical mechanical control elements in the case of the displacement-based trigger type. But there are also control element technologies that offer a high trigger work that are not purely mechanical, such as control elements based on electromagnetic actuators or so-called magneto-rheological fluids/particles. Thirdly, it is clear that the topic of this presentation becomes less relevant when truly self-driving cars are a reality. If that is the case, the significance of the distraction of the user will likely change. In this slide, I will list some of the shortcomings of my presentation. Shortcoming number 1 is that I assume that the presentation is opinionated. I may have a bias toward haptics because I am a haptics engineer. Shortcoming number 2 is that I am pretty sure that I oversimplified the kinetic energy example in section 4. In addition, I used a very specific example, my own body. Instead, I should have looked into percentile-based population data, for example, the span between the so-called 95th percentile man and the 5th percentile woman. Shortcoming number 3 is that I consider an incomplete set of aspects in the design of an automotive user interface. Aspects that I did not discuss but that are also important are, for example, economics and marketing. Before we reach the end, please enjoy a 20-second demonstration of what level of skill a human can achieve with a physical displacement-based and 3-dimensional user interface. Credit goes to the YouTube user Rousseau. This concludes my presentation. If you are interested, then please check out the PDF version of this slide deck, link in the description below. It contains all the references that I used, some bonus content, and a making of.